So today I'm trying to just give a flavor of this basic statistics in most in very, very basic level, but I know that you in previous sessions, you have already gone through many of those concepts, but this particular one will be trying to almost repeat those concepts, but taking a slightly different route rather than showing you slides about what they mean, but I'll take an interactive tour to those concepts. So hopefully it will help you to recap those concepts, and those are quite important because almost like building blocks of developing your further more complex model. So coming back to the very, very basic idea about why we need statistics. So the statistics, of course, the first objective is to describe the data, to give some sort of capture the flavor of the data that we have collected. But the second objective of statistics is more important, which is that the way we try to capture the populations, from where we collected our samples. So what we do in most scenarios, that we have a population, a really large sample for a particular objective. Let's say it could be body weight, it could be systolic blood pressures. It's depending on your research objective. There's a large group of individuals there, but the problem is we cannot measure each and every individuals in that population. So for our medical statistics context, it's most of the time this individual is basically patients or the human being, but depending on the subject's specializations, it could be animals, it could be insects, it could be plants, it could be, the population could be anything. But it's mainly based on your research area, you define your population. And most of the time, the population is too big that we cannot really measure each and every unit of the population, experimental unit of the population. So what we do, we use some sort of random sampling concept or the random sampling framework. There are lots of different methodologies to do the random samplings. I'm not going to that way, but generally, random sampling means each and every experimental unit in this population will have equal chance of being selected. And if we do that, then we can create a sample with a given reasonable size that we can do given our resource, maybe time, cost, manpower, and other resources. Now, once we do that, then of course, there's the first objective that I mentioned. Then we want to try to describe that the samples of the data that we collected. And that's we generally do by some of this location parameter that you know that many of the location parameter, which could be even minimum, maximum values. Let's say we are interested about the body weight. So I'll give it one example, and I'll try to follow that more or less in this other example, also the same example. So let's say we are interested about what is the mean body weight of 6-year-old. So maybe government is quite keen about obesity in this young or those primary school going kids. So the 6-year-old, maybe there's 100,000 individuals in a big city. And then they may be interested that what is the mean body weight of that young kids. So the body weight is our body weight of the 6-year-old, that's our population context. And let's say we collect 100 individuals, we randomly select 100 individuals from that population. So once we have those 100 individuals as a sample, we can try to get some sort of summary statistics of that sample, which is sometimes also called exploitative data analysis. Generally, we use these locations and dispersion, these two statistics. The location could be minimum value, maximum value, but generally it is the mean. Mean is the location statistics that's mostly important, but there's also lots of other location statistics like first quartile, second quartile, third quartile. And the second one is about the dispersion statistics, which again could be range, minimum, max, minus, mean, or it could be interquartile range. But one important dispersion statistics is the standard deviation. So that's the way we sort of summarize or we describe our sample, do our exploratory data analysis. But then another second objective is to use that sample to infer about the population. Now, in this scenario, there is a concept of the sample statistics. So here we are interested about the mean body weight. So the sample statistic is also sometimes called the estimates, which we generally use the English letter like X bar, and the sample variance, let's say S square. So we use this X bar, which is a sample estimate, to infer about the population parameter. So the population mean, that mean body weight in the population, that's generally represented by the Greek letter, which is the mu. So our objective is to use X bar to infer about the mu. So that's the whole our basis. And now we'll see how the statistical principles or those statistical mechanisms can really help in inferring using that X bar, how we can infer about the mu. So that's the most of the things that we do in statistics is based on that basic principle. So to do that interactively, I'll now just use some interactive tool here. So here just I have captured the same thing. So to just do it more, so to just see that is the statistical principles that's really working well, or it's really doing what it is meant to do. Let's say that we know, let's assume here that we know the truth. So of course, in reality, we'll never know the truth because the sensor, I mean, it's generally the census when only we'll measure all the individuals in the population. But again, census is not sometimes directed towards a particular research objective. But for the timing, let's assume that we know the truth. Let's say the mean body weight of all those individuals in the population is 20 kg. And of course, it is the body weight, so we can assume also the distribution is normal. And the standard deviation is the 4 kg. So here, almost I'm defining that I know the truth of the population, and then I'll see how these statistical mechanisms can help us to infer. So once we know the truth, we know how the inferential framework is working. So statisticians use one technique like the random sampling that I mentioned, is that simulations is quite helpful for testing many of these principles. So either we do through mathematical way of deriving this or solving some equations, or use the simulation tools to see what's happening in real world or what could happen in real world. So here, what I did, exactly that I mentioned, I just selected 50 samples. So that means in that populations, I'm selecting 50 kids, and then I'm doing that, measure those mean and standard deviations of that. So these are my 50 kids from that population. And as you can see, some of them are as low as, it's quite small, maybe around 10 or so. And there could be some of them are quite high. And this average is around 20.62. But of course, we know the truth here. So we can see it is slightly deviating from the true population mean. But the thing is that if we just generate again, we'll get another sample. So it is not that there's any problem with the random sampling, but the point is there's always some sort of uncertainty about this, because each and every individual has the equal chance of getting selected. So if we do again another 50 samples, we may get a slightly different sample. And that may happen every time I'll go to the population and collect samples. So that means we have now 2 issues actually. So we started with one, but actually we have 2 issues. First thing is that if we do sampling again and again, we'll get slightly different values. So there will be some sort of uncertainty in our estimate of the sample statistic, which is sample mean. And then, of course, we have to then sort out that how we can use that sample mean to infer about the population mean. So to do that, let's say, and this is the one important concept about the frequentist framework. So the frequentist framework suggests that under identical sampling condition, under identical experimental condition, you can repeat an experiment infinite number of times. And that's the most of the statistical tools that we use. That's the one school of thought is using the frequentist framework. And there's another school of thought is called Bayesian framework, which is slightly different. But what we'll be discussing today is mostly within that frequentist framework. So that means in frequentist framework, we can repeat that experiment infinite number of times. So let's repeat that experiment 100 times. So I've selected 100 here and just do it again. This time, this is my first, let's say first sample, which is saying 19.72 is my sample mean. Now, if I go here, this one is capturing the first 8 samples, but then of course there's all 100 out there. So of course it is not presenting here, but that you can see. The first one, 19.72, I know, but the second one, 20.23, 19.95, so on and so forth. So you can see that there's that uncertainty in each of the sampling, and then uncertainty in those sample mean estimates, we can see quite clearly happening. So that means there is some sort of variability of that sample mean. And what we can do on that. So we have to do something about capturing that variability of the sample mean. So it looks like that all the 100 sample mean, now if we take together, let's say if we have enough resources and we could really do all those 100 sampling, although in reality we'll never do that, but let's say if we can do that and if we get all those 100 sample mean and create a histogram or just do a density, create the density function, then a certain shape will come. And I think you are quite familiar with this shape, which is the normal distribution shape. Although it is not exactly normal distribution as you are seeing here, but you can see that shape is emerging here. So of course, if we take a more number and if we just do it again, that shape will be formulating more clearly. So that means that the sample mean, if you take large number of time, the sample mean, the distribution of the sample mean will follow a normal distribution. And the mean of the normal distribution will be, as you can see here, mean of all those, so here of course 880, so mean of those, all those 880 sample mean is equal to 20. Now, if you remember, our truth is the true population mean is 20. So that means mean of all those infinite number of sample mean will be equal to the true population mean. And that's in statistical sense is sometimes also called as the unbiased estimate. Unbiased estimate. So sometimes it is also mentioned that sample mean as an unbiased estimator of the population mean. So if it is at all possible to do infinite number of sampling, or let's say if I'm doing 1,000 sampling, and if I do it, then actually our mean of all those 1,000 sample mean will be equal to population mean. Of course, we will never do that, but the things that we have to know, what is the then uncertainty in our measurements of that one sample mean? If we can capture that, then at least what we can say, this could be the population mean, but with that uncertainty measurements, we can mention that. So this uncertainty of that measurements of the sample mean, or what is the standard deviation, the variability of the sample mean, as we have seen here in that normal distribution scenario, that can be captured, or that is called as a standard error. So if I just go back to the slides again. So this is what mathematically is very, very easy to prove that if you want to get the standard deviation of the sample mean, so that can be represented by sigma by root n. That means you take the population standard deviation and you divide by square root of the number in the sample. So that means number of individuals in your sample. So that's a really nice and simple way. That means you just do one sampling and then you use that formula to understand what is the standard deviation or the variability of your sample mean. Almost like whatever this frequency framework will say, what could happen in your infinite number of sampling process. So sometimes when you don't know the population standard deviation sigma, we can replace that population standard deviation with sample standard deviation S. Okay, so the standard deviation, standard error provides a measure of how far from the true population value the estimate is likely to be. So that's a quite nice and nice way. Just we'll do the one experiment and we'll get the summary statistics of that experiment, and then that itself could be quite helpful to understand about the sampling variability or the standard deviation of the sample mean. That's good. So at least we now know the sample mean and that's the standard deviation using the standard error concept. Now, and that shorts out what will happen those frequency few, it doesn't really matter having those different sample mean. Now, the second question that still remains, that how we can say about the population parameter, that our population mean. Now that concept is coming from the confidence interval. So the inference about this your population mean, generally there are two ways we can statistically we can deal with. One is the confidence interval approach, and then later on I'll be talking about the hypothesis testing approach. So let's go to the before talking about the confidence interval, what it means, let's just look at the formula. Again, the statisticians or most of these methodological things, they have given a really simple, straightforward formula how to calculate the confidence interval. So let's understand this, what's the formula, and then we'll go back to what is the concept. So just like the standard error mean, we have seen there's also a formula for calculating confidence intervals. So calculating the confidence interval for any sample estimate, you just take the sample estimate and then add and subtract the standard error of that sample estimate and multiply it with the critical value. So for example, in this particular case, we know the sample mean. We have just calculated the standard error of that mean, and then we multiply with 1.96. Now 1.96 comes from the 5% critical value from the normal distributions. If you know about this normal distribution, it's quite symmetric. So 2.5% lower and upper tail. That will, if you see the quantile of that, it will be 1.96. So that's why this 1.96. So sometimes, roughly, even you can say this 2. So and the standard of mean, we know it is represented by sigma by root n. It's basically a calculation of confidence interval is really simple. You take this. You calculate your standard error, multiply with 1.96, and add and subtract with sample mean. So again, coming back to our frequencies concept, let me just put it for the 100 to make it a little bit easier to read. Okay, let it be 90. Yeah. Okay. So if you remember, our frequencies view that we could have 100 samples, samples, each of sample size of 50. So that means, again, we could calculate mean and standard error each time, and then we can use that formula to calculate the confidence interval. And if we do that, then we can actually have 100 confidence interval, right? So, and if we just put this 100 confidence interval, and the 95% confidence interval states that if you can calculate this 100 confidence interval, then 95 of those confidence interval will include the true mean. Now, we know the true mean again here, which is that 20, which is that red horizontal line here. And you can see that here, of course, here it has just come exactly as 95%, but it will just on average that will happen. But as you can see that this first three and possibly this last two, these two are outside that doesn't really include that red horizontal line. And the rest of all the other confidence interval that includes the horizontal line, that red line. So 95% confidence interval means if you repeat the experiment 100 times and every time you calculate 95% confidence interval, then 95 of those 95% confidence interval will include the true mean. So as I mentioned, it's 95%. So if I just do it again, it is now 97%. So, but on average, that's what will happen. So that's the concept of the confidence interval. And now we can see that means the concept of confidence interval is really giving us the meaning of the sum of this inferential framework. That means how we can say about the true population mean, what is the boundary that where it could include on this 95% confidence interval range. So that's why it is sometimes quite useful. And so in some way, it is also, as we'll see later also, it is sometimes more useful rather than the standard way of representation of the hypothesis testing through p-value. So we'll come back to that later, but that's the main concept about the confidence interval and standard error of sample statistics from the frequentist framework. Now, as I mentioned before, that generally the second approach of doing that inference about that, going from talking about the population parameter from the sample statistics, the second approach is the hypothesis testing. So how do we do that, or why we do that? So again, the basic framework is same. We have a population, and then we get samples. So here I have used the same thing. We just again assume that we know the true population mean, so that I can show that how the hypothesis testing is working, or is it really working or not. So we know so here I'm just assuming we know the true population mean, and we know also the population standard deviations, the 4, which is 4. So 20, which is the true population mean, and true population standard deviation 4. And if I just pick up it, so this is one of the samples, and my sample size is 100 here. So this is one of my samples, and all those bars represents each individual. So all of those 100 individuals. Now, before going into exactly the hypothesis testing scenario, let's take a look about there are some steps in hypothesis testing. Now, depending on the different literature textbook, you'll see the steps differ. How many? Some will say 4, some 10. It doesn't really matter. These are the more or less the standard approach to hypothesis testing. So, as I mentioned, this is also the inferential framework. We want to infer, or we want to say something about the population parameter. So, the first step in this hypothesis testing is you have to identify the parameter of interest. Of course, here we know which is our population mean mu. The step 2 is to formulate some hypothesis, and that's why it is called hypothesis testing. So we have to formulate actually 2 hypotheses, but generally these are, once you formulate one, you can formulate the other one also at the same time. And this is called null and alternative hypothesis. So null hypothesis, we sort of assume what could be the population parameter values. So in this case, we assume some population parameter value, or we may have some sort of understanding or some sort of justifications of that this could be the population parameter value. So let's say we just consider that our null hypothesis, our population parameter is 21 kg. And then you set your alternative hypothesis that generally this my alternative hypothesis that it is not 21 kg. So when you define this as a not 21 kg, then it could be greater than 21 kg or it could be less than 21. And that's the concept about the two-tailed test. So generally in most scenarios, we favor we advocate two-tailed test rather than one-tailed test, because before collecting any samples, we generally, or even after collecting samples, we generally cannot really, we generally don't know which directions our alternative hypothesis should be. Because of course, in certain scenarios, maybe let's say if you're using giving some drug for reducing the blood pressure, you know it should reduce. But again, even in those scenarios also, we just don't know beforehand which direction. It could increase the blood pressure, maybe because of some patient characteristics. So in most scenarios, we generally do two-tailed test, which basically means our alternative hypothesis can go both directions. It could be greater than or less than. And that's why it is then not equal to 21 kg. So that's the concept about null and alternative hypothesis. So null means there is no difference, or that's the of course, the null and alternative hypothesis can get more complicated in a complex experimental design scenario. But given our very simple scenario that we are talking right now, that we want to infer about what is the mean body weight of 6-year-old. This is my simple null hypothesis that I defined null hypothesis to be 21, and then I'll collect samples, and my alternative hypothesis is not 21. Step 3 is to, you have to define some level of significance. The type 1 error is also called type 1 error or alpha. And generally it is set as 5%. It is generally quite standard in medical statistics and many other fields, but it depends on the subject area, of course. For example, in physics, it is much smaller than that. For example, remember when the boson was discovered in Large Hadron Collider, there were, I think, p-value was like 10 to the minus 12 or so, or this alpha. So the alpha is really subject specific, but in our medical statistics is 0.05 or 5% is quite common setting of the type 1 error. And then we, of course, collect our sample data and we estimate the parameter, or we get an estimate of the parameter. Now, remember, these 3 steps, we really set even before collecting the samples. So we identify our parameter of interest, we set our null and alternative hypothesis and our type 1 error, even before collecting our data. And that's quite important, because if we set, let's say, type 1 error as 0.01, that you really set before you're collecting the data. Or even if you set type 1 error as 10%, that's also fine, but that you should really set before collecting the data. What is not generally acceptable, you change your type 1 error after observing the data. Okay, so our step 4 is to get an estimate of the parameter. And as we know, the sample mean is a good estimator of the population mean. So we know how to calculate that. You just take all of them, take the values, sum them, and divide by number of observations in your sample. And then the step 5 is an important one, we have to get the observed test statistic. Now, what is that test statistic? It's generally a statistician already gone through lots of simulations and the mathematical calculation to identify for each experimental design scenario or experimental condition, what will be the test statistic. Now, for this very simple scenario where we know the population standard deviation or population variance, the test statistics is basically most of the time, of course, the statistic is calculated as whatever your estimate minus whatever your hypothesized mean and divided by standard error. Again, that's very, very simple scenario. So like this is the sample mean that we have collected. What is my hypothesized mean, which is mu0, and divide by standard error. So which will give me a test statistic, which I mentioned here as Z observed. Now, the statistician again identified that for this particular statistics in this particular design scenario, what will be the distribution of the test statistic? And again, there are a lot of distributions coming there, and we apply that particular distributions depending on this particular experimental conditions. Here, this test statistics follow the standard normal distribution. So we have to identify or to choose, but of course, most of the time it is already predefined. So we know for this given conditions, what distribution that our test statistic will follow. So this is the distribution or standard normal distributions. And then of course, once we calculate the test statistics and we know the distribution, then you have to take a decision that whether the data are consistent with the null hypothesis or not. So let's get back to our examples, and let's see what it actually means, all those tests. It means it looks like a little bit more theoretical, but actually what it means in a real scenario, what you do. So if you remember, then that means, of course, you don't have to remember all the steps, but if I just follow again, so this is the first, we defined our sample, we have identified our parameter of interest, which is the mu. And then our null and alternative hypothesis says that mu equal to 21. So I'll hypothesize population mean, I set it as 21. So our mu 0 equal to 21. Okay, I can set it at any other value, 22 or 23, whatever I like, but let's say I set it at 21. And in this scenario, of course, I know the true population mean. So our first step is our parameter of interest is the population mean mu. Second step is the hypothesized value that we set here is at 21. And then our step 3, if you remember, which is the setting the type 1 error. So which is again, I set it as 0.05, but you can change it to 0.01 or 0.1 or whatever you think. So that's my step 3. Step 4 is I'll collect data. So I have considered that I'll collect 100 samples. So these are the 100 individuals from my population. So this is my step 4. And then step 5 is that, so before going to step 5, I have to, of course, they do our exploratory data analysis. So I can see this is my data just presented in 2 different ways, but this is the box plot and showing that my mean is 20.08 and standard deviation is 4.23. But of course, as you know, as you have seen before, if we do it again, it will come back with some different value. So that's my step 4. We calculate the sample statistics, here is the sample mean. And my step 5 will be to calculate the test statistic. So calculating the test statistic is that formula, if you remember, there's a x bar minus your null hypothesized mean and then divided by standard error of that mean. So we know all those formulas, so we can do that. Now, this test statistic we got minus 2.4. Okay. So then, of course, we have already shown that our step 6, if you remember, that on the distribution of the test statistics, as I mentioned, that follows a normal distribution, which is this curve. And now the most important step is that final step, is that where my observed test statistic lie. This minus 2.4 is that vertical red line, right? Now, here is the important cause. So this is my mu equal to 21 and alternative hypothesis mu not equal to 21. Now, the important thing is, now what is this distribution mean? What is this normal distribution? And as I mentioned, if you remember, it is the distribution of the test statistics. So there are 2 concepts now. What test statistics mean and what is the distribution of the test statistic mean. Now, given that test statistics is actually telling me, so if you remember the formula, it is whatever your observed mean. If I just go back again to the formula, what is your observed sample mean you are getting from the sample data and what you are hypothesized. some way, as you can see here, it is sort of capturing how far your observed mean is from your hypothesized data. It is somewhere taking how far or how close they are, and this standard error is just basically scaling this information. Now, that's the test study. So you get some idea. It is telling me something about how far or how close my observed sample mean to the population mean, or my not population mean, my hypothesized mean. Now, what this distribution says? Now, this distribution is telling me if the null hypothesis is true, if my null hypothesis is true, what should be the distribution of the test statistics? So if the null hypothesis is true, this should be the distribution of the test statistic. And now this red vertical bar is telling me what is the observed test statistic. And then what we do, we calculate what is the probability that this is the observed test statistics. What is the probability that if the null hypothesis is true, what is the probability? So probability that the null hypothesis is true, or probability that our hypothesized value is 21, given that we have observed samples, what is the probability? And that one is telling me is the probability is 0.0164. Now it is a very small probability. So that means this is something like this right-hand side of this red curve, and it's basically 2 times of that. Now, this dotted vertical one, this red regions, as you can see, this is my type 1 error. So 2.5% here and 2.5% here. And as I mentioned before collecting data, we don't know which scale it will lie. It could be this line could be this side, or this could be that side, depending on whatever direction it is going. Now, this is showing this line is this side, but it's in the red region. Now, type 1 error is saying us that if the null hypothesis is true, and if we reject this, if you reject the null hypothesis, what will happen? If the null hypothesis is true, and if we reject it, that means we are committing some error. We are committing error when null hypothesis is true and we are rejecting it. And that's why this is called type 1 error. So what level of error that we can accept here? So here, that's the setting. So that means we can only afford 5%. That means if we repeat this, again, this frequentist concept, if we repeat this experiments 100 times, and if the null hypothesis is true, we can afford that 5 times we reject the null hypothesis when it is true. Now, this is telling that our probability here is 0.0164. So that means if we repeat the experiments 100 times, and if the null hypothesis is true, given whatever we have seen, observed data we have, the probability of rejecting the null hypothesis will be around 1. If it is true, it is 1.64, which is basically less than what we can afford to commit that level of mistakes. So basically it means that we can afford less than 5%. That's our limit. And because it is committing less than 5%, so we'll say here, we reject the null hypothesis. So, or we'll say the evidence based on our observed sample data, we have evidence against the null hypothesis and we reject it. So you can think about, it is almost like the criminal proceedings or court case scenarios that we do, where there is an accused, and which is always generally think of presumed innocent. And then what we do, police or other investigating agency, they collect evidence. So the accused is presumed innocence, and then collect evidence like sample data or other type of evidence, and then find out what is the probability that this accused is innocent given this data, observed data, or given the evidence. Now, if the probability is really small, then we can say that we have evidence or beyond reasonable doubt. That's a court statement generally they produce, that beyond reasonable doubt that the accused is innocent. So that means a very small probability that the accused is innocent. So that means we basically say alternative hypothesis true, or we accept that accused is not innocent, or accused has committed some crime or other things. The same concept here also. So if null hypothesis is true, what is the probability that we observe this data? Probability of observing data means if you see in the statistical literature, it will say like probability of observing the data or as large if the null hypothesis is true. So, but basically it means we are trying to find out that this probability, if we based on the statistics, if it's small enough, then we can say that we reject this null hypothesis. Now, this is a let's just say if we do again, let's say hypothesis, we know the truth here. So if we just update again and see what is happening in this scenario, that because we know the truth, of course, but we can go back to the population and see it is showing 20.12. So test statistics and other things are showing. Your test statistics is 0.3 and p-value is 0.76. So that means the probability is 7.76 means it is now that p-value that we have, or the type 1 error that we have set up, which is 5%, it is now greater than that. So now we can say that we do not have evidence against the null hypothesis. So we cannot reject the null hypothesis. So in this scenario, we will not reject the null hypothesis. Now, you should be a little bit careful sometimes about the statement. So it's not correct to say we accept the null hypothesis, because in reality, accepting null hypothesis is not really this correct statement. The reason being that if you really, it means you can think about it intuitively also, it makes sense. But if you have a really large samples, and because this whole statistics is also that's a denominator standard error. So even if it is a really small difference, you can still make it significant just because making a standard error very, very small. So rather you should say we do not have evidence, or we do not reject the null hypothesis, or we cannot reject the null hypothesis. That's the proper statement rather than saying accepting the null hypothesis. So it should not say accepting null hypothesis. Now, I'll just come back to another concept about so I'll just make it 21 and get this statistics here minus 2.15. Now, using that, the previous concept that you have got about the calculating the confidence interval, so we can get also the confidence interval here also. Now here, the confidence interval is the difference. So is exactly this x bar minus mu, that difference, and calculating the confidence interval. So which is captured here in the top. Now, the 1.1 you can see here. So this is the confidence interval is ranging from minus 1.64 to minus 0.08. Now, when the confidence interval will include 0, so that means we do not reject the null hypothesis. Now you can see 0 is lying here. In this scenario, the 0 is outside this your calculation of confidence interval. So we can say here, we can reject the null hypothesis. So now basically you will see this, both of these two informations will give you the similar conclusion. So for example, here is the p-value is 0.03, which is less than the type 1 error that I can accept to commit. So that means I reject the null hypothesis. But the alternative way to see that, you can calculate the confidence interval, and this calculation of confidence interval exactly we follow the same formula that we have used before, but only difference here. Previously, I mentioned only for the x bar, but this time it is the difference of mean. The only difference is here, the difference of mean and its confidence interval. Now, if the means are equal, it should be equal to 0. So that's what, but of course there's uncertainty, so we can capture that confidence interval with that long, this two tail and lower and upper. Now, this doesn't link to 0, so that means we can say, so whatever we have considered here, so it's a 95% confidence interval does not include 0, so that means we reject the null hypothesis. Just contrast that with the same way. If we have this 20 here, and this time the p-value is 0.54, and you can see that it is greater than 0.05, so we do not reject the null hypothesis. And this is my confidence interval. It includes minus 1.02 to 0.54, and you can see that it includes the 0. So that means we again coming to the same conclusion that we cannot reject the null hypothesis. So it's the both ways that it'll give you the same conclusion. Now, for presenting your results in the literature, in your paper or in your manuscript, a better way of representing it is through confidence interval. Now, because the confidence interval, so if you see the p-value is just giving those probability if the null hypothesis is true. What it is not telling us anything about what is the magnitude directions of that effect size. So for example, this one is telling me what is the magnitude? It's a minus 0.24. So it gives us also the directions, the negative sign. So of course, when you have more complex experiment, we are also interested in the effect size. Its magnitude direction of that effect size is quite important. And this precision, for example, if the confidence interval is narrow, it's more precise. If it is very wide, it's less precise. So getting that magnitude direction and the precision of your estimate is well captured by this confidence interval rather than p-value. The p-value in that way is not very meaningful. So when you will present your results, it's quite important that you present p-value along with your the confidence interval, 95% confidence interval. I think I'm getting very close to 54. So should I just close here? And then means it's just one topic. I'll just go very quickly if you want. So is that so the first one basically, if I just recap very quickly, we considered about the sampling distributions and then showed that how the frequentist view of sampling, and then showed the sample estimate, the distribution of the sample statistic, in this case, or distribution of sample mean. One thing I forgot to mention here is that distribution, that sample mean is following a normal distribution. It's actually quite nice property. It's also called central limit theorem, that if you have a large sample, and if you really repeat that sample infinite number of times, that this distribution of the sample mean will follow normal distribution. And it's actually true for whatever the distribution of your original sample. So it doesn't necessarily important that this original population should be normally distributed. Rather, if you have a large enough sample size, then the sample statistic, distribution of the sample statistic will follow the normal distribution, so, which is a quite nice property. And many of these statistical methodologies are built on those particular central theorem property. And then we have already got an understanding about the confidence interval, what it means. And then we are into the second way of inferring, which is the inferential framework using the hypothesis testing scenario, which defined that what is the, we use the null hypothesis and alternative hypothesis. And then of course we have found that there is a couple of steps to go through, eventually which will link to a statistic. And then we'll follow the distribution if the null hypothesis is true. And then we'll see where my observed statistic lie. If the observed statistics is very small, that means we have evidence against the null hypothesis, because there's a very small probability that the null hypothesis is true. And then, of course, we mentioned that the confidence interval is an important way of presenting your results. Now, before doing any experiment, particularly, we are interested to capture that. So, for example, here, So let's say, again, I'll do that. So 21. So for example, here you can see we are not really rejecting the null hypothesis. So of course this could come because of one thing could be that our, but of course here we know the truth. So one issue could be either it is type 1 error, or we didn't really collect enough samples which will have which will have enough statistical power to capture the difference properly. So that's quite important, and that actually we have to do even before doing or before collecting data. So for any experimental design or any experimental work, we have to think about what sample size we need to find the difference if it exists. Now, type 1 error I mentioned, type 1 error you do, or the level of significance or alpha we do when we actually, after collecting data, we test against the null hypothesis. But the type 2 error, there is another error. So type 1 error, if the null hypothesis is true and you reject it, then we commit type 1 error. But type 2 error, if your alternative hypothesis is true and you reject it, then we commit the type 2 error. Now, that's what most of the time, let's say we have a new medicine and we feel that it will reduce the blood pressure. But we do need to plan our experiment with enough sample size, because it's not enough, because eventually when we'll be doing the hypothesis testing, we should have adequate sample to capture that. So what we don't want, we want to commit type 2 error. So even if the null hypothesis is not true, or alternative hypothesis is true, and if we still reject it, that will not be very helpful. So here is a very quick way to, again, using the same phenomena, but of course it's again very simple framework for doing the sample size calculation. So we identify sample size, so sort of saying what sample size we need to achieve a statistical power or experimental power. So here, for example, we define what is the mean value under the null hypothesis true, and what is your or our alternative hypothesis. So we want to design an experiment to find a difference of 2 or more. So if it is of course bigger, then we can still find the difference. So that one we have to define. So just a very quick recap about things that we need for the sample size calculations or getting a statistical power. Of course, we may be interested to get the sample size calculation. The things that we need is the variability of the outcome variable, like in your body weight case, we know that's the variability or your standard deviation. And then mean difference, this is quite important. How big the difference that you are interested in means, for example, again, the blood pressure examples. Do you feel that 10 millimeter mercury, that's the big enough difference that a new drug, if it is there, that will be clinically significant? So for example, if it is reducing by 2 millimeter mercury, even if you prove that is significant, it may not be clinically relevant. So that mean difference, which is clinically relevant, that's important. So that you have to define beforehand. And then of course, level of significance, the type 1 error, and then type 2 error or statistical. This is generally 80% or 90% that is kept as standard. So just go very quickly to our, so here I mentioned the null hypothesis 20. So I want to find out, I want to design an experiment so that I find out a difference of 2 or more. So I put my alternative hypothesis 2. I know the standard deviation is 4 or 6 is variance. Type 1 error, I set it as 0.05. Type 2 error, I can set it as 80%. So just let's keep it at 80%. Now, on the concept of, again, if you have already understood this previous hypothesis test scenario, where this red region is the type 1 error, it's exactly the same. Here is, it looks like the orange region is a type 1 error. So this is the distribution of your under the null hypothesis. This is what you are expecting or under the alternative hypothesis, right? So this is my difference. Now, this is the type 1 error, and this blue region is the type 2 error. So type 2 error means, if you remember, if the alternative hypothesis is true and we are rejecting it. Now, think about this. This cyan or blue region is actually from this distribution, from this distribution on the right. But if you see, this is my type 1 error. So all those blue regions, if we collect data, we'll say this is actually from this distribution. So we'll reject this, although alternative hypothesis is true, but we'll say this is there is no evidence. So we'll commit it type 2 error here. So that means we want this cyan region to be as small as possible. And this, so to get that, so here, for example, it is showing, if you want to get a mean difference of 2 with a standard deviation 4 with the alpha means type 1 error 5, you need 25 with 80% power. Now, our main point is, so the 80% power is that you will get a 25, you need 25 samples. And this is the alternative view also. You can fix the sample size and see what will be the power. So it looks like if you have only 15 samples, your power, statistical power will be 61%. So you can see 61% is quite big. So this whole cyan region is almost like 40%. So the 61% is this, and this is 40%. So that means, as you can see, we have really less power. So almost half of this, like 40%, although it is belonging to this alternative hypothesis, but we will sort of say we do not have evidence. So we'll commit type 2 error. So all the time, what you really want, now the problem is that, so for example, if I show you, like if I increase this, let's say difference, so you can see now we have increased this or decreased that cyan region. So that means if we have a difference of 9 kT, then of course we can find that there's we need of course it says showing this. So if you have a really big difference you want to capture, then you can see that our statistical power is quite high because most of the things are at this side. But that means if you're really trying to find a very small difference, like let's say getting to 20 to 23, that means we really need more and more samples to get there. So as we, and you can see intuitively it makes sense. Smaller difference you want to capture, then you need bigger sample. So the way to handle that, then that means if you need, if your differences is big, then you need less sample. And other way means if your differences is small, you need more samples. And it will also depend on the standard deviation. That means if you have a really small standard deviation, you can capture, or you will need small sample because you will have a higher precision of your estimate. So for example, it's 4, and if I do it as 3, you'll see the sample size now reduced. But if I increase it to a very high, you'll see the sample size now, you need a quite bigger sample. So I think that more or less very quickly to cover some of these different concepts of the very, very basic statistical principles and the terminologies. Hopefully that was useful. So I'll just stop here, but I'm happy to take any questions if you have.
I'm muted. Thank you so much. That was indeed very, very insightful. And I know for sure I'll be using this recording and coming back to it when and as I need it for my own projects. This is very useful to know that it's there. So yeah, anyone, any questions, either just type them in the chat or directly put on your microphones, ask us questions. The feedback form has been posted in the chat, and we would really appreciate if you could give us some feedback. And we will wait for a few minutes in case anyone has any questions that they might not have thought of just yet. Dr. Nath, in case anyone has any questions afterwards, are you happy to share your email with the students?
Yeah, that's fine. You can share my email. Yeah. That's good.
Okay, perfect.